For IB, we need to look at some irregularities in the ionization energy trend. So let's consider, for example, period 2. Period 2 begins right here and goes from lithium up to neon. If I labeled them as I went across, it'd be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. And generally, that ionization energy is creeping upward and going up and up and up. But you'll notice there's two hitches in here. There's a hitch there and there's a hitch there. Similarly, if I look at group 3, which goes from sodium to argon, I will find similar hitches. There's one there and there's one there where it doesn't keep increasing. To understand what's going on, I want to look at the electron configurations of these to decide which electrons are being removed. So looking at beryllium, that's its electron configuration. For boron, that's its electron configuration. If I'm looking at which electron is being removed, in beryllium, it's this electron. But in boron, it's that electron. And the number of protons increased and it's pulling hard on them, but the fact that it comes from a different subshell makes a difference. The reason why is the 2p is a higher energy level than the 2s, making it slightly easier to remove that electron than to remove beryllium's electron. We see a similar pattern in going from magnesium to aluminum. The difference there is magnesium ends in 3s2 and aluminum ends in 3s2, 3p1. Same idea, we're removing the electron from the 3p instead of the 3s. And when it's a higher energy level, it's easier to remove if the number of protons is the same. Here, the number of protons changed a little bit, but not enough to offset the difference in the change of energy level. We also need to look at the difference between nitrogen and oxygen, which is going to be analogous to the difference between phosphorus and sulfur. So over here, phosphorus, sulfur. So looking at nitrogen, 1s2, 2s2, 2p3. Oxygen, 1s2, 2s2, 2p4. I need to look at their orbital diagrams to see a little bit more. The orbital diagram for phosphorus. Up, up, up. For oxygen, up, 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 down. The electron that I'm removing is here and is here. So now the difference has to do with whether they're paired or unpaired. So this is an unpaired electron. And this is a paired electron. The paired electron ends up being slightly easier to remove because it's somewhat repelled by this other one. And so the way that I would explain this is the paired 2p electron in oxygen is repelled slightly by its other electron, making it just a little bit easier to remove than nitrogen's unpaired electron. And once again, this would be the same explanation that we would have if we were trying to explain why sulfur's ionization energy, first ionization energy, isn't higher than that of phosphorus.